I'm a grad student at the University of Colorado at Boulder, and today I'll be talking about retrieval methods and algorithms for retrieving thermospheric density and temperature from SUVI solar occultations, and I'll be presenting some preliminary measurements from these algorithms as well. So first, jumping into a little bit of background and motivation on this project. Currently, there are no real-time measurements of the thermospheric state, and this is kind of a problem because the neutral densities, they have the largest impact on satellite drag, and particularly for satellites in low Earth orbit, this is a problem. Current drag models, they use geophysical forcing indices such as KP, AP, and the F10.7 radial flux in order to predict what the neutral densities are doing, and then they use satellite trajectories and their drag in order to update these models. But these satellite trajectories, they have a rather high latency of 2 to 4 days and aren't really good for using them in space weather operations for forecasting and nowcasting. And so there are a couple other ways to get neutral measurements in the thermosphere, such as mass spectroscopy. However, another method is ultraviolet limb measurements. And these have been a proven method, and they're particularly nice because they can be done remotely, and you don't have to actually be in the thermosphere experiencing this drag to get thermospheric measurements. And so the motivation of this project is to get a real-time measurement of the thermospheric state for use in space weather operations. And the GOES R series satellites are a perfect candidate for this sort of research because the GOES R series satellites made by NOAA, they're already an operational space weather platform, and they have an instrument on board called the Solar Ultraviolet Irradiance Imager, and it is an imager that is taking images of the sun constantly, tracking the sun's morphology as it relates to space weather. And GOES, it undergoes 2 occultation seasons per year around the fall and spring equinoxes. And these occultation seasons last about 45 days, and we get 2 occultation measurements per day, one on the dawn side and on the dusk side, during which SUVI is still imaging the sun as it goes into occultations and looking through Earth's atmosphere on the limb. And we can use that to get the transmission through the Earth's atmosphere to use for modeling the Earth's thermosphere. So we've already seen some images or graphics of what solar occultations look like, but for SUVI specifically, because it's an imager, the full solar disk is projected into the terminator plane. And when it's projected into the terminator plane, we get about 300 kilometers of spatial span in the thermosphere. And when we project the SUVI imager, its pixel scale into the terminator and the thermosphere, we have about 0.5 kilometer resolution just from pixel to pixel. And SUVI measures at 6 different wavelengths. In the extreme ultraviolet, we can use 4 of them, the 195, 171, 284, and 304 angstrom channels because they have a high enough signal to noise during occultations. And they're always measured on a fixed measurement schedule. And so during the about 2-minute occultation period, we're able to get measurements from multiple channels, and this allows us to resolve between the major species in Earth's thermosphere, which are atomic oxygen and molecular nitrogen. And so now I'll go into the retrieval methods on how we use these occultation images to get atmospheric parameters in the thermosphere. This is kind of done in 2 different stages. We have first the registration of the SUVI images into the terminator for what region of the atmosphere we're actually looking at. And then the other part is taking these transmission images and using them in a forward model to get atmospheric temperature and densities in the thermosphere. So as I mentioned, first we need to get the transmission profile, and this starts with an occultation image on SUVI shown here. And in order to get the transmission, we need to know the state of the sun, and we use the most recent non-occulted image, what I call the topside image. And taking the ratio of this occulted image to the topside image gives us a transmission profile image shown here. And then the next part is figuring out what section of the atmosphere we're looking at. So we use the location mapping on the sun that Sewell gives us in its data files, and we back project that into the terminator plane in order to get this scaling shown here, where you have altitude on the y-axis and latitude on the x-axis. And so this together is our extinction ratio image, or our transmission image. And then to improve our signal to noise from these images, we actually collapse this down into a 1D profile where it's just a function of altitude. And here's an example from a given occultation on Sewell where we have measurements from all 4 of the channels that we use. And the solid lines are what Sewell actually measured, and the dashed lines are from the empirical EMSIS model. So what it would say is the transmission for that given day. So obviously there's some sort of discrepancy here, and what we're trying to do with our next forward model steps is to figure out what the atmospheric parameters are that would generate these extinction profiles. So as I mentioned, we do this through a forward model in which we need to produce a realistic thermospheric density and temperature, and then create a transmission profile to compare to our measured transmission profiles on Sewell. And this is done first by constructing a temperature profile. It's common in the thermosphere to use a Bates temperature profile, which is a simple heat conduction equation where we have the exospheric temperature, the temperature at the very top of the atmosphere, and this decays exponentially as a function of geopotential height and is shaped with these 2 shaping parameters, A and tau, which are just constants for a given day. And then we use this Bates temperature profile to create a number density. Here in the thermosphere, we can assume diffusive equilibrium, and it's given by this equation here, where it's dependent on the scale height of a given species, and then this Bates temperature profile, and then this n sub s for every species. It's a reference number density, and I'll talk more about that a little bit later. But then we also use the column density, and this is the actual line of sight that density that Sewell is seeing between the satellite and the sun. And for this, we can use an Abel transform in which we assume spherically symmetric shells of atmosphere, and then we integrate across those shells for the line of sight. And this gives us the column density. And then we can calculate the extinction ratio, which is the same thing that we're measuring on Sewell, which is related to this column density as well as the absorption cross-section for a given species at the channel that Sewell is measuring on. So obviously those equations I showed are a set of nonlinear equations, and whenever you're doing nonlinear least square solving, these methods are often very sensitive to seed values. So we've worked pretty extensively getting good seed values that are also self-consistent with just our measurements. And so first, in order to do this for the temperature profile, we are able to calculate the exospheric temperature, that temperature that's at the very top of the atmosphere. We do this by inverting the extinction ratio profile for either the 171 or the 195 channel. And we do this because the cross sections of O and N2 are very similar at these wavelengths. So it looks like the absorption of the total mass density rather than a weighted sum of either of the O or N2 densities. And so by inverting this extinction ratio profile, the slope at the very top of the atmosphere looks like the scale height of just atomic oxygen, because that's what's predominant at the top of the atmosphere. And so we get the exospheric temperature from this equation here, just relating simply the slope to the scale height of oxygen. And then the only thing that's not self-consistent in these seed values are getting our A and tau shaping parameters for the Bates temperature profile. What we do for this is we take our fitted exospheric temperature, but then we use a database. Here we're using EMSIS, but we could use another database that relates the temperature to these shaping parameters. But we get the average A and tau values for a given exospheric temperature that we have fitted. And so now with these seed values, we're able to construct a full seed temperature profile, which we can then use to retrieve those reference O and N2 number densities that I was referencing earlier. We do this for O first by using that temperature profile to construct an O-only column density profile. So using that scale height at the very top of the atmosphere, we project that down through the atmosphere that we have measurements for. And so using that column density, then we take the inverse of that Abel transform that I showed you earlier in order to go from column density to number density. And we interpolate that into a reference altitude of 300 kilometers, where we expect there to be a lot of atomic oxygen in the thermosphere. Lastly, we need to get the N2 seed number density at some reference altitude for our diffusive equilibrium equation. For this, we subtract the measured extinction ratio from the O constructed only column density extinction ratio in this equation shown on the far side. And then once again, we take the, that should say, inverse Abel transform to go from column density to number density, and we choose a reference altitude of 250 kilometers, where we expect there to be more N2. So this is a summary of all of that I just talked about. We take those seed values that we just found, and we construct our thermospheric temperature Bates profile, and we also construct our number density profile for O and N2 using that equation for diffusive equilibrium. Then we integrate these number densities along Suvie's line of sight in order to get column density using the Abel transform. And then we use the absorption cross sections of O and N2 at the Suvie channels that we have measurements for a given occultation to create a synthetic extinction ratio profile. We then compare that to the measured extinction ratio profiles that we found before, and we iterate this process until we have the best temperature profile and number density profile that fit our measured extinction ratios. So jumping quickly through some preliminary measurements that we have from these methods. Here's just an example data product that we have. So once again, we have the O number density and the N2 number density. Here they're just simply compared to the EMSIS model. And then we have our Bates temperature profile through the thermosphere, also compared to what the EMSIS Bates temperature profile gives. Because we are measuring 45 continuous days during an occultation season, we can also look at the climatology of the thermosphere during this range. And here, once again, it's compared to EMSIS, which are these small green diamonds, and our measured data are these black stars. And we can see that the overall climatology of our data, it matches that of the empirical model and climatological model, EMSIS, but it has more of that day-to-day variability that you would expect from real measurements, and that we would want to see for a real-time space weather data set. And lastly, because we're talking about space weather, here is a storm time event during the fall of 2018. There were actually 2 geomagnetic storms seen in the storm time index. And here in our data, we can see that the N2 densities were enhanced during these storms and the O densities were depleted. And this is something that you see in our data, but not in the EMSIS data, which is driven by still geophysical indices. And this would obviously lead to enhancements in the ionosphere and would be important for space weather. And so this is a good case for using this in space weather forecasting and nowcasting. So the future of Suvie occultations, as I've been hinting through this, we're trying to get this into a real-time data pipeline. We're working with NOAA and their branch of the National Centers of Environmental Information to get this incorporated into the real-time Suvie data pipeline. And this should be available on the NCAI website this summer, and with the first real-time measurements happening during the fall occultation season of 2023. Another thing we're doing is we're doing comparisons to general circulation models, specifically TIE GCM. And then we're also working to get this into assimilation models, specifically IDEA, which is a GCM assimilative model, and then a drag model called Dragster. And here are my conclusions. As we've talked about, there's no real-time measurements of the thermospheric state. What we're trying to do is we're trying to change that using Suvie solar occultations. These measurements will date back to 2018 when the GOES R series satellites first came online and should be available through the mid-2030s for real-time use. We've discussed the algorithms. I won't go more into that, but this pipeline should be available this summer with real-time data happening in fall of 2023. So lastly, I'd like to thank my advisor, Ed Tiemann, as well as all of the SUVI occultation team for all the help that they've done with this work. I'd also like to acknowledge the NASA Space Weather Operations to Research grant that this was funded under. And I'd like to thank you all for listening today.